Okay, today we're going to look at 5.4, which is all about visualizing these exponential functions. So what we want to do is use that C and A that define an exponential function to understand how that changes the visualization of the exponential function. So far, right, we know that in general, growth kind of looks like this, and decay kind of looks like this, but how does that shift around, and how does that change? When does it grow faster or slower? How is that affected by those two values that define the function, the growth factor and the initial value? So just as a reminder, any exponential function, right, is C times A, to the X, where A is always going to be a number greater than 0, and it's not going to be 1, because if it was 1, 1 to any power is just 1, and we won't see exponential growth. So if C is positive, which is the only kind of initial values we worked with, and the only kind of initial values we'll continue to work with, the only thing we want to remember here is that if A is greater than 1, then we've got growth, and if A is between 0 and 1, we have decay. All right, so what we're going to explore today is, what do these exponential functions look like? What's pretty consistent about how these functions, how we can visualize these functions? So overall, the first thing we want to talk about when thinking about those visualizations in the graph is domain and range. So the first thing I want you to think about here is domain. So remember, domain is always your input value, x. So in this general form of the function, are there any types of x values you can think of that you wouldn't be able to plug in? So is there any type of exponent I can't have? And the answer here is no. We can plug in anything we want for x. If you think back to 4.2 and 4.3, we can have fractions as exponents. Those just mean powers and roots. That means we can have decimals. That means we can have anything positive or negative. We know that negative exponents just mean we're dividing by that number. We can have 0. Anything to the 0 power is 1. So there's nothing that doesn't make sense to plug in here. So we don't have to worry about our x values. We can plug in anything we want and get a domain from negative infinity to positive infinity for any exponential function. But the interesting thing here is when we think about what outputs are possible. So we can plug in anything we want for x, but as we think about plugging in those negative numbers or positive numbers, we have to think about what's happening to y. So if we think about exponential growth, right, in this first function, so we're just going to play around with some values and see if we can figure out if we can have any output or if there's going to be some restriction here. This first function we're going to look at is just an example of an exponential growth function. So we remember exponential growth, it looks like this, right? So as we have x values, we can see we're getting anything positive here. It makes sense to get any positive outputs here as we think about plugging in x values into the function. That just gets bigger and bigger and bigger. We can get any positive y values that we want. Starting at x equals 0, we can get that output of 1. But what we want to think about is, okay, what's happening as we go this way? Because it kind of looks like the function in exponential growth is leveling off as we go off to negative infinity. And we want to see if it is in fact doing that, or if it's just going really slowly towards negative numbers. So we're going to explore x values that go really just towards negative infinity, so we can explore what happens with our function. Okay, so plug these x values into your y equals 2 to the x function. So for x equals -1, we see as we start to move past positive numbers and into negative numbers here as inputs, 2 to the -1 does not make that number negative, right? 2 to the -1 is 1/2. So here, we're getting to something smaller than that input of 0. We're getting to something at 1/2. And if we move into -50, again, that doesn't make my output negative. That just means I'm going to divide by 2 50 times. And in that case, if I go ahead and plug that into my calculator, it'll give me a scientific notation number. It'll tell me that that's 8.9 times 10 to the -16th, a very small number. If I do keep going towards negative infinity, y equals 2 to the -200, then I'm going to divide by 2 200 times now, If you plug that into your calculator, you get about 6.2 times 10 to the negative 61, an incredibly small number. And something kind of interesting happens here, at least on some calculators. Try plugging in negative 1,000 there. My calculator, my graphing calculator that can save a lot of information, right, tells me that this equals 0. But we know that that's not true because we know that 2 to the negative 1,000 is 1 over 2 to the 1,000th power. We're just dividing by 2 so many times that that number gets so close to 0, our calculator can't handle all those zeros basically, and just tells us it's 0. But we know this is just really close to 0. It's not actually 0. So as you see this pattern here, negative exponents will not give me negative numbers. They just give me smaller and smaller numbers as that exponent gets to be a bigger and bigger negative number. So with exponential growth, we are seeing that graph level off, and it's leveling off. It's just getting really close to 0, but we'll never make it to 0 because there's no x that I can plug in to this function to get an output of 0. Even if I plug in 0, I get an output of 1. So it'll just approach 0, but never get there. Now that's exponential growth, and we know exponential growth and exponential decay work very similarly. But with exponential decay, we see it going up to positive infinity as we move into those negative x values. Now, as we move into the big positive x values, that's where we're seeing it approach what looks like now to be 0. So we want to test that here. Here's a decay function. We want to make x bigger and bigger and test those values and see if you again approach 0. And it turns out you will. In fact, we're finding the exact same numbers we did before, right? Because 2 to the negative 1 is the same thing as 1/2 to the first power. It's just 1/2. And 1/2 to the 50th power is the same thing as 1 over 2 to the 50th power. Okay, this is the same thing as 8.9 times 10 to the negative 16. 1/2 to the 200th power is just 1 over 2 to the 200th power. We'll get the same thing, 6.2 times 10 to the negative 61. And this one again, when you plug in 1/2 to the 1,000th power, if your calculator isn't just really beefed up and can hold all that data, it'll tell you it's 0, and we just know it gets really close to 0. It is not equal to 0, even though our calculator wants to tell us it is. Okay, so again, we are going to approach 0 on this exponential decay, but this time as x gets bigger and bigger, showing that decay. So what this does to our visualization of exponential functions is it creates what's called a horizontal asymptote at that y equals 0 output. A horizontal asymptote, and it does this for both growth and decay, right? Just in different directions for growth and decay. That horizontal asymptote is just a line, right? Y equals 0 is a line that the graph approaches, but it will never actually get to. We're just going to get really, really close to 0, but we're never actually going to get an output of 0. There's no way for us to take a positive number to an exponent and get a negative output. All right, so that's the first thing that we realize about the visualizations of exponential functions. So what we want to do now is say, okay, so in general, here's some exponential functions I've graphed. And in general, these are all doing the same thing, right? These are growth. They're all approaching 0, just at different rates as I go to the left. And they're all growing exponentially as we go to the right. So what we want to identify now is what's creating that difference in the rate of change. What's making the green one go up faster than the blue one go up faster than the red one. And so we're going to investigate. These 3 graphs were created from these 3 equations above. We're going to use 5 points and see if we can identify with these 5 points, match them to the graph, and see if we can tell which graph is which. So go ahead and pause the video, get some good practice plugging in exponential functions into your calculator. Plug in -4 for x, -2, 0, 2, and 4 into each one of these functions. Get 5 points and then match them to the graphs. Tell me which one of these is the green graph. Is it 100 times 1.2 to the x, 100 times 1.3 to the x, or 100 times 1.4 to the x? What we're doing here is investigating that effective A. Notice I'm leaving the initial value the same for each one of these. Okay, so go ahead and pause, see if you can get these numbers, and I'll fill them in here too. So you should have gotten, you'll have to do a little bit of rounding, 48.22 here, 69.44 here, 100 when you plug in 0, 144 when you plug in 2, and about 207.36 when you plug in 4. Keep going, we'll get 35.01 on this one, 59.17, 100, 169, and then 285.61. On the last one, you should get 26.03 approximately, 51.02 approximately, 100, 196, and then 384.16 approximately again, right? All of those decimal ones were rounded. So just look at the relationship between these numbers here. Notice with the 1.2 to the x, and notice with all of these functions that they all have the same point at 0. But as we start to move backwards into the negative x's, the 1.2 compared to the 1.3 decays slower than this one. And this one decays even faster. Sorry, I was like confusing if 51 was greater than 59 there for a second. Yes, absolutely. This one's decaying faster, right? As you move into -4, this one's 48. This one went down further to 35, and this one went down even further to 26. So they're decaying faster as that A gets larger, and it's also growing faster as A gets larger. So if we look at these graphs, what we'll see is that this first one that is growing faster and decaying faster to the left, it's both growing and decaying faster, has the highest A value. This one matches with 100 times 1.4 to the x. The one in the middle is the one with the A value in the middle. It has the middle level of growth and decay. And the one at the end has the slowest growth and decay with the lowest A factor. So what we're seeing there is that the effective A is the greater the A value, the faster the growth and the faster the decay. So we can visualize those functions. Okay, so let's try it with decay. What happens when we have decay in all of these and we start to change that A value around again? So again, I'm going to leave C alone. I'm just going to pick a steady C value. And I'm going to see, okay, I see with exponential decay that some of these are going to decay slower and grow slower. What's going to cause that change? Is it going to be similar to the relationship we had with growth, or is it going to be a little bit different? So again, take some time to pause and fill in these tables and see if you can match and find that relationship for yourself between what's happening as that that decay factor gets larger or smaller. For this one, you should have gotten about 3,333.33 for -1, 1,000 for 0, 300 for 1, and 27 for 3. Again, all of these zeros will be the same because all the initial values, the C's, are the same for these functions. But what happens when I change from 0.3 to 0.5? As I go in the negative direction, I decay slower, right? I only go down to 2,000 rather than 3,000. As I move into 0.7, I go down even slower. I only go down to about 1,400. Oops, yeah, that's right. As I go positive on the 0.5 compared to the 0.3 decay factor, I grow faster. Sorry, I don't grow faster. I'm still decaying, 1,000 to 500, confusing myself here. I decay slower, right? I went from 1,000 down all the way to 300 with 0.3, but I only go down to 500 with 0.5. And then as I move into an X value of 3, I only go down to 125 rather than going all the way down to 27. With 0.7 getting an even bigger decay factor, I go down to only 700 with a move of x to 1, and only down to 490 with a move of x of 3. So actually it turns out, right, that our decay is happening slower for a higher decay factor, and our decay is happening faster for a smaller decay factor. And that makes sense because the smaller the number is, if I multiply something by 0.3, I'm going to only have 30% of it left, rather than if I multiply something by 0.7, I'll still have 70% of that original left, I'll have more left. So if you think about those decay factors in percents, that makes sense. So did you match these up correctly? The one that decays the slowest, the green one, should be y equals 1000 times 0.7x. Decaying slower means you have a higher decay factor. Decaying the fastest means you have the lowest decay factor, the smallest decay factor. And that one at 0.5 just sits in the middle between those two decay factors. Okay, so that kind of almost happens in reverse, right? The bigger the growth factor, the faster the growth. However, the smaller the decay factor, the faster the decay. And we'll summarize that here in this summary, okay? So let me say that one more time. For growth, we have that the larger A becomes, the faster the growth. And we like that larger makes the growth faster. But the reverse happens for decay. The smaller A becomes, that means we have less percentage to keep, the faster the decay. All right, so visualizing those functions there. So we can say immediately if decay is slower, then it must have a bigger decay factor. The last thing we want to do, and you've probably already seen this looking at the graphs before this, is what's going to happen if we change C. So let's leave this alone. The same thing's going to happen with C, whether or not this is growth or decay. So let's focus in on growth. We're comparing 3 growth functions with the same growth factor, but different C values. So again, see if you can match these to their correct graphs by finding 3 points for each and matching up those points on the graph. With the first one, as you plug in x equals -1, you should get 2.5. X equals 0 is 5. We have that initial value of 5 here. And then we get 10 as we plug in 1. For a C value of 20 with the growth factor of 2, you get 10, 20, and then 40. And with a growth factor of 2 but an initial value of 40, you get 20, 40, and then 80. So right there, we can determine which graph is which by just looking at the initial value. So the 5 had an initial value of 5, so that must be this graph down here, y equals 5 times 2 to the x. This one is the one in the middle with a y-intercept of 20, y equals 20 times 2 to the x. And this one is the one with the highest y-intercept at y equals 40 times 2 to the x. So very similar to lines, if I change the initial value, it's easy to differentiate between which graph is which. But what's interesting here is it looks like somehow that the C value is affecting the growth, right? Doesn't it look like the green line is increasing faster than the blue line, and that the blue line is increasing faster than that red line? And that's not true because we know that the growth factor affects the growth. So what we're seeing here is just that this growth has been shifted. So let me kind of clear this so I can highlight the changes I mean here. So these are all the same. So these are all growing at the same rate. We're just looking at different segments of each. So it's kind of like with this first one here, we're looking at the blue line at just the beginning part here. It's just this line shifted down. And this part of the red line, sorry, I don't know if I'm explaining this very well, but basically they're just shifted around, okay? So it's just that this growth is happening later for this line. Eventually it'll grow like this one is right here, just later on. And this one is kind of like this graph just back here, right? So they're only shifted around, even though kind of visually it looks like that C value is affecting the growth, it is not. It's just shifting that growth around. Only the growth factor determines how fast that line goes up. Okay, so the main part here, even if that was a little confusing, sorry about that, changing C only changes where the function crosses that y-axis. It only changes the y-intercept. It does not change how fast the function grows. Okay, so let's put that all together. So we have an exponential function. C gives where the line crosses the y-axis. A determines that growth or the steepness of the graph. For exponential growth, we have that the larger A is, the faster the growth. If we have decay, we have that the smaller A is, the faster the decay. We also saw from the very beginning that exponential graphs have horizontal asymptotes. For exponential growth, we have that as x goes to negative infinity, y approaches 0, right? Think about that exponential growth graph. As we go off to negative infinity, that's where we're approaching 0. For exponential decay, we saw that the reverse happens, right? For decay, as we go off to positive infinity, that's where y approaches 0. So see if you can't put all of that together. And I've got 4 graphs here that'll match these 4 functions. Can you tell which graph is which equation matches which graph by just using the differences between those C and A values? So let's see if you got it right. First of all, I would find C, because C is the only one with a different C value. So it's going to cross the y-axis at 10, where all the other ones are going to cross at 5. The only one of these graphs that crosses at 10 is this one down here. So this is C. Now, if we look at these graphs, we see that this one should definitely be decay, because it has that, the factor is between 0 and 1. Here we see 5 over 2, but we remember 5 over 2 to the negative 1 is 2 over 5. So again, this one is decay. This one is the only one that's growth. So now we can eliminate D and say, okay, the only one that's growth is right here, so that is D. So growth versus decay also is a big player in this game. Now notice our scales are the same on all of these graphs. So what we're seeing is that these 2 top ones are both showing the same snapshot of the equation, and we have one that is decaying much faster than the one on the left. So this one is decaying faster than this one. So we need to figure out, okay, decay happens faster the smaller the decay factor. So is 2/5 smaller than 0.7, or is 0.7 smaller than 2/5? If you think about 2/5 as a decimal, this is 0.4. So the smaller decay factor is the faster decay. So this one is B and this one is A. The slower the decay, the bigger the growth factor. So this is a growth factor of 0.7. This is the growth factor. Sorry, I said growth both times. Decay factor of 0.7 and decay factor of 0.4. So it really helps us understand the difference between all of these graphs and the visualizations of them. All right, guys, give that homework a try. Let me know if you have questions. Take all of these different things into account, right? We got a really good summary of them up here, and see if you can figure out just some general graphs from those differences between A and C.